right, so let's get started. So first, before we start, a couple of questions. So who actually here do some native development? Or is a man? Yeah, okay, cool, cool. Who's using Gradle for native development? Right, and who's the other people? Are you thinking of using Gradle for native? Yeah, okay, cool, awesome. So my name is Daniel Lacasse. I joined Gradle last October, specifically to help improving the native development. So you're all in good hand. This presentation will revolve around correct and flexible native build by default. So a bit about me, I'm from Ottawa, the French part, if you can tell. I'm an open source enthusiast. I'm a native and C++ developer by trade. I have a huge passion for automation, and my second passion is skydiving, so you can tell from the picture. If you need any information during the talk, if there's anything you don't understand, please raise your hand. We'll address the question as it goes, simply because we'll be building up on examples. And obviously, if you don't understand the first part, it will be hard to understand the second part. So the agenda today will be breaking on 4 parts. So first, we'll start with an overview of the history of the native development in Gradle. Then we'll walk through some examples in Gradle for native development. We're going to explore 2 automation patterns in native, and then finally we'll look at the future of this native support. Some history. Prior to version 1.7, which we call legacy, there was extremely limited configurability, really simple DSL, and you could only support and build the shared library and executable. And then in 2013, we got a sponsorship for the initial development of native, which brought in toolchain configuration, platforms, flavors, Visual Studio support, test suites, all that jazz. That was roughly from 1.7 to 1.11. Then in 2014, roughly version 1.12 to 2.3, the support for Objective-C and C++ was provided by a community, pull requests, and then the support for some unit testing framework, introduction of the software model, which we're going to see later, and some improvement to the cross-compilation in Gradle. Then in 2015, we got some parallel compilation done. We got some improvement to the software model, notably the addition of the rule engine and the managed type, support for precompile headers, and also Google test support, which was again another community-driven effort. Last year, from version 2.12 to 3.3, and there was another round of improvement to the rule engine. There was the build dependent and Visual Studio 2015 support, again added by the community. So a huge thank for the community for all the awesome features they're providing us and helping us develop and add. So Gradle native support use what we call the software model. Before we go too much into detail, we'll look at some of the classic Gradle first. Before, what we would use with Gradle, what we use in Java, is the configuration would be done on the task itself. Gradle does a good job of presenting the task configuration in a model-like look, if we may. So if we look at here, like line 5, 13, and 18, we get jar, test, and upload archives. Those are all tasks. So it looked kind of like a DSL, but really configuring the task itself. And then the applied plugin would generate the task graph that we see right to on the right side. With the software model approach, it's a little bit different. In a nutshell, the software model describes how a piece of software is built and the other component it needs as dependency in the process. We'll go in a little bit more detail later on in the coming slides, but the design was driven by the community feedback and also from the day-to-day problem user faced. Basically, when a plugin would be applied, it provide a model element, which we're going to see soon in the coming slides, and it will apply rules and conventions. Most configuration is done in the configuring the model block that we call, and it's all about writing rules in there. It's much more declarative. The code size is similar to what we have with the Java side, so the current model, except it produced this enormous graph. It's a much more complex task graph. So what we get is the model plus the rules plus the convention that the plugins are providing, and that will generate a task graph. The model is really all about the configuration of the task. In the end, we still use a task graph at execution time for driving the native, basically, for the build. So let's walk through a simple example, and we'll build on this one. So here's a minimal working C++ build script without any dependency. The first thing we notice is the apply CPP plugin on the top. Basically, that's if you're familiar to Gradle, it's pretty familiar. It's the same thing as you would apply Java. The plugin will shape the project by adding capability to it. In this case, we're adding a C++ capability to the project, as well as some core native model element and containers. There's other plugin that exists to add other language. We're talking about assembly, C, Objective-C, Objective-C++, Windows resource. Those plugins can be mixed in to add those capability in, depending on what actually you want for your project. It also supplies some standard toolchain support, which we're going to see a little bit later. Now comes the big difference from the current model. The configuration of the native build is really about writing rules in the model DSL, which is the little bit highlighted there. The rule engine will take care after that and during configuration time to parse all those rules and run the right rules to it. We won't go too much in detail about how the rule engine works exactly. There's a wonderful workshop online on the Gradle YouTube page. It's called Rule-Based Model Configuration Workshop. It's a 2-part video. Extremely useful if you need to learn a little bit more about how to write those rules. But in a nutshell, the rule engine will create a DAG that will be run at configuration time. It's kind of the task graph, but at configuration time. And everything is inside the model block. It's all rules. It doesn't feel like it, but it is rules. They are translated as rules. So what is a rule? A rule is a piece of code that's going to mutate a subject with the help of 0 or more inputs. All the subject and the input are basically model node, model element from the model, from software model, basically. The cool thing with the rule engine is that all the inputs will be fully configured before they're passed to the rules. And the subject that you're modifying will, the subject will, you won't be able to read on it. You can only modify it. And the inputs, obviously, you cannot modify them. You only can read from them. That's kind of what the rule engine kind of enforce. In the model block, we declare what we call groovy style rules. And it's only available, you can only declare them inside the model block. What do we mean by groovy style rules? That it has special syntax to be able to specify inputs to your rules. We're going to see that a little bit later. If you want to share your logic and write rules in a plugin, you would usually go down the route in the Java style rules, which is usually specifying the documentation of rule source. So for all that kind of things, the Java style rules are outside the scope of this talk, so I would suggest you read the documentation about rule source. Amazing, really well documented. The rules are lazily executed. That means that if something is not needed at execution time, it's just not going to configure it, and your rules won't get executed. New plugins, well, other plugins can provide new model element that can then be used inside the rules as input and as subjects. Before we go a little bit further, it's important to make a pit stop here to explain the two major containers in Gradle. If you use Gradle before, you're already exposed to the domain object containers. For example, the configuration or the source sets. Those are two containers that's heavily used in the Java world. Those containers are used everywhere in Gradle. It's the bread and butter of all the DSL that Gradle creates. So the domain object container, they always have one type of things inside of them. You can apply rules to them to be able to modify them. We're talking about the all rules, the name by name rule, so the element in there that you can modify, the matching. These containers are what we call live collection. That means that it will evolve as your script configure. There will be more things that's going to be added in there. Those rules that we just specified there, the all and the matching, those are are kind of listener that's going to attach the container. It's going to be applied to all past element, the element that you're adding now, and all the future element that's going to be added to your container. So it's important to make the distinction between the all and the matching rules, and also the .each and the for all, the find all, which are more standard iteration or function to be able to on a collection. Those kind of eagerly resolve the container, and sometimes that's not what you want. In the example on the right side, we see that there's the configuration DSL, which is a domain object container that contain configuration objects. So we see in the first part at the top, when we want to create new element, we can create element by passing no configuration block, just the name, and that's going to create an element in there. Or we can pass a configuration block that at creation it's going to configure, execute at closure, is going to configure it with whatever configuration you want. On the second part of the example there, this is when you want to configure an already existing element. So there's three ways you can do it. Either by property access, so you can specify the name of the element and then the property you want to modify, and you add the value there. Either with a configuration block similar to how you created, or you can also use what we call the domain property access, the container property access. So every element in the container can be accessed as if it was a property of that container through their name. The second type of container is called the polymorphic container. The native support in Gradle heavily depends on those type of container. They contain lots of different types of element. They have the same operation as you would get on a domain object container, with the added rules of the with type. The with type will take a subset of the container for that specific type. And again, that subset will also be live. So that means that if you do each on it, you're only going to get the element at the point you do each. If you do all, then it's going to be for all for every subsequent thing that's get added in there. When you create an element in there, you'll have to specify the name and also as the type for it. Since there's several types, you kind of need to guide the container of what type you want to add. In the example on the right, you see there's a components container, which is a polymorphic container. And again, two-part, the creation, you see that you can again do the same thing similar to the other container. You can specify the name and the type, but without any configuration block, or you can specify a configuration block to it. When you configure them, again, same kind of idea, the name of the element and then the property you want to modify, or a configuration block. As you can see, during the configuration of an existing element, you don't need to specify the type, as the container already knows what's the type of that object. So if we go back to our example here, we see that the first model element that we're going to see is the components. A component is a set of source that represents something that we want to produce. In the case of native, we're producing binaries. Some model element will participate in what we call the dimension of a component. Those dimensions create binary variant, and then that's where it becomes a little bit more complicated, and that's why the software model was created for solving this problem. We can see here that we create the new component by name, again the name element that we call main, and the type of the element, we want to create a native executable, so it will be a native executable spec. There's a second also native component that we can use, which is native library spec for creating static and shared library. The names for all those elements are project unique, but they can be also overridden by the base name if you don't want to change the name of the end artifact that's been created. Native support also have the concept of language. The source set model is really there for configurability, to be able to configure where your source are and all the source that participate in building that component. It represents a set of source and headers of a particular language. Could be C, C++, assembly, whatever you want. Each component and binaries can be associated with one or more language source set. By default, each language plugin will add one language source set to the component. So in this example, we applied the C++ plugins, so the C++, the CPP source set is already created, and if we want to configure it, we don't need to specify any type, it's just there, it already exists. This is a conventional source set that we call. The location of those source set by convention, the location of the source will be source, the name of the component, and then the name of the language source set. It can be changed if you want, and there you can just change it. You can also add more language. In this case, we're adding a second one, which we call generated, and it will be a C++ source set. And then we configure it by saying, well, we want the source set to be generated by a task. There's additional source set that you can create. It's again, just like polymorphic container, as I said previously, it's heavily used in native. The different source set are supported are right there at the bottom. Maybe it's a little bit hard for people in the back, but it's assembly source set, C source set, CPP source set, Objective-C, Objective-CPP, and Windows resource. The build type is what we call free-form dimension. There's no real structure to it. You can define it for basically anything you want. But conventionally, we use it for debug, release, debug optimize, final, whatever you use in an organization. For each component will generate a binary variant for each build type. By default, the build type is that's created is debug. It's named debug, but there's no, like I said, there's no real structure to it. It's just a name, and you put the meaning that you want to it. As soon as you add elements in there, the debug by default will just go away. So if you'll have to add the debug on your own if you want to add it. Another dimension to all the component is what we call the platform. Platform is a combination of the architecture and the operating system that you're targeting. Architecture can be ARM, Spark, AMD 64, OS, obviously Windows, Linux, Mac OS X. In the future, we want to model more than that. We want to model the ABI, the C runtime, and much more than that in there. But at the present moment, it's really just the architecture and the operating system. By default, if you don't specify any platform, it will be the default, the current platform that you're running on, the current architecture and the current our operating system. So in this example, we have 64-bit. We specify the architecture to be x64. The current operating system, we don't specify any, so it will be the current system that you will be building, so invoking Gradle on. And then the other one, we're specifying an ARM platform, so architecture ARM and operating system Linux. It's kind of like cross-compiling, or if you run Gradle on ARM, which I don't think it's done, but whatever, it's doable. Just a little note here. We see that like I put quote around the 64-bit. This is because Gradle tries to be really awesome at creating DSL and easy to use things. However, sometimes Groovy will get confused and will think otherwise. In this case, the tokenizer just think that 64 and bit are separate things, and it gets confused and Groovy complains. I really like the name, so when that happens, sometimes that happens, you just put quote on around it and it will put Groovy back in place. It happens sometime when we use a keyword. That happened one time when I did the build type and I wanted to be really have a build type called final, but final is a name, a reserved word in Groovy, so putting quote around it solved the problem. Sometimes it can be like just difficult. You're trying out and then Groovy just don't want to cooperate with you and show you an error, but it's not an error. Also, for each platform, we need to be explicit what we're targeting. So in this case, we want the main component to be able to target both 64-bit and ARM, so we have to specify 64-bit and ARM. By default, the component always target the default platform. Toolchain doesn't really participate in any component dimension. Gradle will select the right toolchain for the platform. Toolchain is responsible for supplying the platform-specific argument. There's 3 types of toolchains supported at this current moment. So we have Visual C++, GCC, and Lang. Creation is, again, same thing as everything else, the polymorphic container, so we specify the name and the type of what we want, and then the configuration block, which is optional if you want. In the case of GCC for ARM, we kind of guide Gradle to tell him that that toolchain can actually target the platform ARM, and then the closure that's follow-up, that just comment in there, that would be the platform-specific argument that you would provide to the toolchain. As we saw a little bit earlier, we see that configuring container element at creation time. That's pretty much what we did so far. But it's important to know that some elements are automatically created for you by convention. One such example is the binary container. The binary container, we expect you to configure the binaries instead of creating them yourself. Because of the rule and the convention that's already in place by the plugin, it will get created automatically for you. So to configure it, it's usually useful for specifying compiler flag or a linker flag or defines and things like that. So there's two ways to kind of be aware. One way, the first one is we take all the binary container, which could be any binary. It could be native or could be anything else. In this case, we really want to address, we configure the native binaries. So we subset the binary container by just grabbing the native binary spec, and then we configure the CPP compiler argument to add the -g. But those rules can also be chained together to be more expressive. In the second example here, we take all the shared library binary, and then we're matching all those shared library binaries for the debug type, and for all of them, we're setting buildables to false, so we don't want them to be built. So they can be chained, they can be mix and match, however you want. Those can also be done directly in an if you want the dot all directly, and then you do if and you split it. Depends how you want to configure it. So let's look at some dependency management in native. First, we'll create two components to make the example a little bit more interesting. So let's declare one called interface and another one called common. The interface will be the API, let's just say the header, and the common will be common code that we're going to share with everybody else. As you can see, again, the interface is quote because I like the name, but unfortunately interface is a reserved word, so that's ways to work around those. So both of those libraries, they will generate static library and shared library. The dependency on your project will be is defined on the binary itself. So in this case, we're going to on the main component, so the executable, and we're going to say the binary we want to depend on the libs and the comment. And then notice the linkage. The linkage is what are we going to consume from those binaries, so from those component. In the first one is linkage API, so we're going to consume the header during the compilation. So everything that's pre-processing, we need the header, so we're going to get the header from the API, the interface. The second one is static. Static is we're going to consume the header plus also during pre-processing, and the static library of during linking. And the one that's not there, which is the default, if you don't specify any linkage, will be shared. And the shared is basically getting the header for pre-processing, and the shared library for runtime, and then the static library of that shared library for linking to the API. Dependency also work across project. You can specify what project you want and then the library in there and all that. In the essence of being correct by default, Gradle allows a build author to query the model. To do so, you use the rules available on the container, and you can also use some standard iteration method, just like normal collection. Usually in those cases, you would kind of, two use cases that present to you. Sometimes you have a binary that you build, a tool that you would build inside your code base, and that tool you'd use it, for example, post-processing some binaries at a later stage. So what you can do is you can actually go and query and find that binary that you want and then use it in an exec task later on in the build. That's one example of querying the model. The other example is sometimes you want to just have a handy task to be able to execute and build a specific subset of binaries that people would usually build and want some handy task to use. So in this example right there, it's more an example of the second case where one handy task to build a subset of binaries. So in the first up there, we want to create a task. So we get the task model element and we specify a creation task, so a creation rule, sorry, with the name and the type, which is a task. And then underneath we see the little $sign with the binaries. That $sign, this is what we call, what I said earlier, where it's a special syntax in the groovy styled rules to say that we want the input, we want an input to our rules, and the input to our rules, we want the binary container to be passed to us. So when this creation rule is going to be executed, the binary container will be fully configured. All the binaries that your project defined will already configure and created. And then so we're going to subset it by grabbing just the native executable binaries. And it's safe at that point to use the .each because the container is already configured. And then we're going to loop through each executable binaries, and then we're going to have some conditional here to say that we want the matching build type to be the release type. And then if that's matched, we're going to add a dependency for that task to be the binary. A more shorthand version of that will be the second example where, again, same idea. We have creation rules, the name, the type. In this case, we want to build all shared libraries. So again, $sign to get the input of the binary with type, all the shared library binary spec. And then we can do a find all, which is kind of the Among Us of the matching part. Except the matching is live as opposed to the find all is really, you just want to iterate through it. And then we pass in a closure to say that anything that is buildable, that's what we want, and we're going to add it as a dependency for that task. So we see beside to the right there, it's a dry run of those both tasks, and you can see the first one, it's only release executable that get task, only the task for those, and in the second one, it's only the shared library that are executed. So we only cover a really small portion of the native support. There's much, much more available in there. I would redirect you all if you want to learn more about how to do it and all. I know like there was a question at the expert panel yesterday about training and things like that. So this is pretty much my answer for training is there's a lot of resource already available in there. So there's talks and workshop, there's the new Gradle model talk, there's the rule-based model configuration workshop that I said previously, there's the Gradle Outstanding C and C++ build system by Gary from last year, and then also the Gradle C and C++ workshop. There's also the user guide. There's 2 chapters in particular that's pretty useful. The rule-based configuration and extending a software model. And also there's this new thing that was just released, which is the growing selection of specialized guide. They're all available at guides.gradle.org. Those are guides, there's some for native, but there's also some for performance and some for other different things like plugin writing and things like that. The next part we're going to look is 2 automation patterns that are really important in the native if you want to simplify your build. So Gradle's flexibility and correctness really comes from the effort that you put into modeling your build logic, and something that you can configure. It's really a work of engineering your build versus scripting your build, the what against the how you want to do it. Gradle is more on the what you want to do as opposed to the how. To the left, it's a typical straightforward implementation of kind of a how you want to do it. Basically, we use the pre-build library. It doesn't really necessarily to be able to read it all, but just to put things in context. The first part, the really tiny part, that's a way that you would probably poorly define what boost is, and by just saying, well, boost is just these header file, but actually boost is more than that. There's certain library under boost that you would need to link against some static library. So if you would go a step further and you want to model everything like that, you would look something similar to the next part where you specify your header and then you have all those condition in there to try to configure all your different static library and shared library. It's a little bit lacking in flexibility when you want to let's say, automate everything and just pull the binaries in from remote repositories or things like that. So the right, like a way to do it, there's not the only way, but it's a better way of doing it. It's really modeling, deep modeling what you're actually trying to do. So on the right side, it's kind of an example of how you could model boost actually in there. So you would have a boost plugin that you would apply, and the boost plugin would provide you with a DSL, the boost DSL. And from the boost DSL, you could ask him, give me a version X, so in this case 1.64. And that would give you a library, a representation of the library on your system. It would take care of locating, the model in there would take care of modeling locating the boost library locally or remotely, if it's a binary distribution or source distribution. And then you can configure, so you can say configure that binary that I want. And that binary it will return you a configure builder type object. And then from there, everything you're going to ask him to do will just take the right decision, because it has a binary, so it knows what architecture you're trying to target for that binary and configure, and what build type and things like that. And then you would get something like with ASIO, which is a boost library, that you would say that binary is taking. And what would that builder-like pattern would do is it would set up the include root properly. It would transitively add boost system, which is required by ASIO, to the linker if required, if you're building actually as something that's statically linked, or something that is linked together into an executable binary. And then it could locate, and like I said previously, locate and build the boost library. And it could also give you meaningful errors in the case for your user. So if your user is trying to use a boost library 1.53 and is trying to use a library that's only available in 1.64, and instead of telling you, instead of letting the compilation goes and at the linking say, well, I cannot find that link, that library, or the header cannot find any header, it could just tell you, well, that library is not available at the version you're trying to use. It's really all about taking taking the knowledge from your build engineers and really giving it and transferring it to your users and to the developers into a less complicated, into a more easy to consume model. So really, the idea is really to focus on the aspect of automation and reproducibility. You optimize time loss by searching those obscure error, that link error that doesn't really mean anything except if you actually know what your build is actually doing, which sometimes doesn't happen with some developers. And also, it's also applicable to more other complex libraries, such as the Windows SDK. If you ever develop for Windows, you get this Windows SDK that is provided handily by the Visual Studio. But unfortunately, sometimes the Visual Studio team would push a new version of the SDK with their updates without you really knowing it, except if you really read all those release notes. And then at some point your build will just fail for no reason because they changed something in the header file. So to avoid this, you kind of model it a little bit more tightly, and you really say what version you want to use, and then after that you don't have any problem of failing on the CI but passing on a user machine, or the opposite if that happened. And then the developer can really focus on what's most important, which is the business line, what you're actually developing, the software that you're developing. And also, when you model things complex as the Windows SDK, there's tools in there that you may want to go and fetch and use into exec task. So having a better modeling of what the Windows SDK is, you can actually go and grab it instead of trying to do some kung fu path mapping and creation at runtime. Gradle is more than just building software. There's a lot of success story of where Gradle does a lot of infrastructure management. At this point, it's really about thinking about the infrastructure as code. For example, there's a Gradle plugin for managing Docker container, for managing Jenkins server, or for managing Vagrant. It's really advantageous for the native developer with regards testing specifically. In a sense, when you build native, there's a lot of variant that get generated. If you just take the architecture x64, x86, and then Windows, Linux, you already had 4 variants that you would most likely need to test on all those systems. So your testing matrix becomes extremely complex really fast. well, not extremely complex, but it become complex, more complex than what it could be. Typically, the complexity is usually pushed onto the developers and for them to figure out their own workflow. You spawn up your own VM to test your things, and then the CI is handled by another team that does this complex thing to synchronize all the slaves. So with Gradle, all the complexity can be moved inside the code and allowing the developer to really concentrate on what they're trying to do and really creating doing what they're best at. So in a sense, Gradle can definitely do things like provisioning a VM, shipping the exe, well, building it obviously yet, but shipping the exe on it, the test suite, running it, pulling the result back, tearing down the resource if it needs, or just reusing it for the next test and all. And then that will all feel like it ran locally. But the cool thing with this is it works for the local machine, for the local developer, but it also works on the CI. The same code can be used for both, for all this testing. And if you go one step further, you can even try to fiddle around inside the provisioning for the locals system to really set up all the debug pipe that needs to be done. And so you can attach your debugger in a handy fashion and really save a lot of time in debugging. You see a failure on the CI, well, you should be expecting that when you run the same task on your machine, it should also be failing so you can debug it. And then if you want to go even one step further, if it fell on CI, it could grab a crash dump for the machine before tearing down and then giving that to the user. So in this sense, Gradle is really powerful task execution, allow you to use those caching mechanisms, the parallel execution, the worker API that we saw in this conference. So Gradle will do all the heavy lifting of figuring out when things got executed. All you need to concentrate is on your specific logic of your testing and what you're trying to achieve with this. So over the next few slides, we're going to look at the future of the native support. By no means this is a roadmap of what we're going to do for the next year. It's just to give you an idea of where we're going in the sense of what we're looking at and moving forward. There's certain work that's already underway, some that may be deferred to next year or the year after, but it's just give you an idea of what we're targeting. So the first thing is really dependency management. A big strength in the Java world is the dependency management, how strong it is. But it was never translated to the native. Native has its own little flower of dependency management, which is pretty rudimentary. So we're committed to improve this situation, and we're laying out a full dependency management. This work is already underway, and we already have some success to it, but really basic success. We've only been working at it for a couple of weeks now. But we're talking about including really transitive dependency with exclusion rules, the remote dependency resolution, artifact publishing to local and remote repository, composite build support for multi-repo. With this effort, we're rolling out the feature right now. So we're looking at little configurability first, and then we're going to add some more configurability. So at first, it's really things need to align correctly so it works. That's what currently in 4.1 milestone 1, but really it's just as an example code. We're keep working on this. And we really want to get the composite build also to be compatible with native. It's been extremely useful in Java world, and we feel that native should really be able to take that feature and really build on it and use it. If you don't know what composite build is, there was a couple talks during this summit, and there's also lots of documentation online. I really suggest to go see the video about this. There's extremely exciting things that's coming on with the composite build. And then there's some work avoidance. The performance improvement can take several forms. We can, aside from optimizing the hotspot in our code base, we're looking at some improvement, some of those improvements. So we get the cache support that we're really looking into. It provides us incredible performance gain in the Java world. So we would like to roll it out and put it in native too. It's a bit more complex than native world, but we're confident that we'll be able to make it work. It's more than just the GCC object file caching that exists. It's really about the task output of the caching. So really, any task that you would have if you specify your input and your output correctly could be cacheable. In the sense, Gradle would in the future would come out with by default native compilation task cache, but for any of your tasks that you create, you should be able also to roll that out. We're looking also at better incremental detection, avoiding static library creation when possible. It's been an effort that's been done on the Java side too, instead of creating the jar and then consuming that jar later on. Same thing with native. We create those static library and then we consume the static library later. But that's like a bottleneck of the compilation. We could definitely go in and just pass in a local build, pass in the object file directly to the next compilation. So we can parallelize a lot more things and wait for less things happening. Also incremental static library creation, and also looking at modeling a little bit deeper the understanding of what native is and those interface, so that non-interface change won't trigger new relink of your application. Certain scenario it works, certain scenario that the object file just change, some symbol just change place, and that caused the relinking. So we're looking at fixing those. There's also some improvement to the build scan. Obviously, right now, don't get me wrong, the build scan are really useful on a lot of things, performance-wise or anything like that. But the one thing that's been lacking for the native is all the test visualization and also dependency management. But with the new work that we're doing, the dependency management will definitely be able to have a look and have an insight directly in the build scan. And test visualization, sorry, my French, will definitely be useful for all the native, for the different build test framework that we're looking at. So the last part that we want to improve this year is really about those software model versus current model things. So the software model goal is to capture the pattern. I know I talk about this throughout this talk, but really the software model goal was to capture the pattern that are similar to all programming language. It was a very ambitious project. There was some performance goal too, as well as solving configuration and ordering issue. We recognize that taking existing build from the current model and migrating to the software model is some significant investment. The decision last year was to backport a lot of the capability of to the current model. As of Gradle 4.0, all GVM capability that was in software model got backported to the current model. So we're talking about variant and platform aware dependency and the distinction between API and implementation. So really the next year is really focusing on this cleanup. It's our ongoing effort that's been going that will be extending through this year. The software model is an aggregation of really 3 key components. You get the rule engine that I spoke. There's the manage type also, the @manage annotation if you are familiar with that. And there's also the multiple component, the component-based configuration. Nothing is finalized yet, but here's the direction we're kind of looking in the converging of the both model. So the first thing is we'll be preferring more a DSL and task-based configuration approach over the rule engine at the present moment. There's a new API that came out, the provider API that came out with 4.0 that really helped with this decision. There will be migration path for anything, build logic and all that, that's heavily utilizing the rule engine, but the decision is really to make the bridging between the two a little bit closer and more aligned with everything else that's happening. The manage type won't be backported initially. We plan to roll out an improved version of the manage type throughout later version of Gradle. But at the current moment, we feel that it's a good thing, but most of it is not a big investment to not backport the manage type at this present moment. The last part is we're opting for better variant support over the multiple component. So we realize that a lot of those components that we create and all that is a lot of them is to bridge the gap of the limitation of the variant declaration that we have in Gradle. So we're looking at improving those. There won't be much change required from the build side. There will be a little bit of layout change, but nothing truly. Code doesn't necessarily need to be moved everywhere because of the convention where the source is. We can point source wherever we want in those aspects. So once we accomplish a little bit more of the work, we'll communicate a migration plan for the software model user to the new effort, more aligned with the other priority that we have or other work that's been done in parallel, such as caching, performance, and composite build. So we're looking at some ways of bridging the two, and really it will be more of a migration as needed to benefit of the new work that we're doing in there. It's really, the software model is really all about the configuration of your build. Everything underneath the test, not the test, but your task, the compilation, the tool chain, everything like that will all stay the same. It's all the same and shared everywhere. It's really about the configuration, how we're going to be. It's most the semantic that's going to change a little bit. Nothing over the top. So we really want people to switch, well, not switch, but the new effort is really going to provide clear value for the next step we're going to do. And we're already in the process of doing it, and at the same time we're cleaning up some limitation that we're seeing and some polishing of things. Previously we developed the compilation, and then we did the IDE integration and testing, and we can see that IDE and testing is a little bit need a little more polishing. So with the new effort, we're looking into setting up the end-to-end process first. So we're talking end-to-end by building, linking, dependency management, composite build, installation, API versus implementation, test framework, build scan, IDE integration, all this long chain, all end-to-end from the beginning. And without too much configuration. It will be pretty static configuration. And then we're going to add configuration. But as we add more configurability to this entire chain, we're going to do it for the entire workflow. So workflow will evolve at the same time, and it will be much more polished than what it was currently. So we're aware of some of the limitation of native, and we really want to improve and want to involve the community a little more. So definitely, if you guys have any edge case or user case that you're already using Gradle and you feel that it's a little bit, it could be better, or I want to do this and I find it's too troublesome to configure it, please provide us, send us issues, send us comments, anything like that. We really want to get those and get it done and add it to our development phase and integration testing to make sure that we support them and we keep supporting them in the future. Because really it's all about like we know lots of limitation, but then again we could spend like a month fixing one limitation, but no one actually cares, and it's just a theoretic limitation. So we don't want that. We really want people to drive us with that. Right now we're really in the effort of cleaning up, like adding dependency management, which is a big feature that people are requesting, but any other things, welcome any of these. And there's this this repo we created. So under the Gradle organization, the Gradle native, this is where all the issue and everything is going to migrate. Right now it's pretty much empty, but it will, after the summit, we'll start migrating all the issue there. It's really to be a native space for people that really are in-depth native and don't want to care about Java, can just like be there and like have fun and talk about native and what can be next. So it will be, initially it's mostly of the issue and what work we're gonna do, so you can follow what we are doing. But later on, we'll start to try to modularize a little bit more the native and move it in its own repo. So it's easier to consume, easier to wrap your head around when you're a new developer and you want to just provide some pull requests or some improvement. So with that, is there any question? Yes?
Just a little confused.
Yes?
So are you saying that the rules engine and the software model are going to be phased out?
Or what, sorry?
Are going to be deprecated and phased out?
Okay, that's a good question. So the question was, is the software model or the rule engine will deprecated? Eventually, they will be phased out. At this present moment, it is not phased out. It is the way to write native. We are working on the new improved of workflow for native, and when we get more work into this, we're going to start coming out with more documentation and what step forward. But the 2.1 will be evolve and connect in some ways, so that you won't have to migrate all or nothing, your entire thing. You'll be able to migrate part of it and benefit for whatever is the new features and then move forward with that.
Does that mean there's going to be no software model for Java support either?
The Java, all the feature for the software model for Java has been moved. All the feature that was developed, especially in the software model, has already been backported to the current model. So everything that's in there is everything that was in the software model is now in the current model. So there's the new plugin called the Java library that came out not so long ago. I think there was a blog post about it saying all the different, specifically like the API versus implementation that they rolled out. The one that's still on the software model, and we're looking into improving that, is the Play framework. That one's going to, there's discussion on what's going to happen with this, but definitely it's not going to be abandoned. We're not going to just stop supporting from day to day. There will be a migration path for that one, but for the only one that's in there, it's really the software model is the only one for the Java side to be on the software model. Yeah, again, they will most likely be coming out with some migration plan for that specifically. Was another question? Yes.
Yes, regarding the dependency management and
Mm-hmm.
transitive dependencies, will that be considered? Will you tie that into the native model directly, or will it be a separate entity from native, such that other programming languages that have the multi-dimensional, like binary variants, other programming languages that have binary variants will be able to use this new dependency management system?
Okay, no, a very good question. The question was, is the native dependency management going to, from the new work we're doing, is it going to cross over with the current software model, and is that new dependency management going to be able to use it in other domain? Is that summarized pretty good your question? Okay, so definitely when we call about the new dependency management with the variant aware and all that, that's a root, like a core feature of Gradle. All the dependency management is dependency, variant aware, platform aware, and all that. That's been rolled out already. There's a usage of that dependency management in Java and in Android to be able to do all the variant aware. In the native, we're going to use the same thing to be able to do all the transitive dependency under the same engine of the dependency management. And that dependency management can also be used on any other thing, any language you would want, any domain, other domain than the native and in Java. It's really about, it's the dependency management section feature in Gradle. It's its own thing. It's not tied necessarily to Java or tied to native. It's its own thing that native is using and Java is using and Android is using. So really, you will be able to do to use it in other language if you want. I think, not too sure, but I think the Go plugin ties in some way into the dependency management too. So that's one example of outside of the realm of native and Java. That answer your question?
Yes, thank you.
No problem. Is there another question? Yes.
So say in C++ something, you change something in a template. How would your plugin, I'm just asking how you plan on doing this in the future. I know you can't tell now, but how in the future would you be able to say these are all the files that need to change because of this?
Yes, this is the improvement for the incremental build, compilation. Right now, it's not well polished yet, but the way Gradle detect how a file has changed is basically parsing the header as its own parser and find all the include. Basically, it's taking all the hash include and just trying to build a graph of the files that are included in the build, but it's not perfect and it could miss some if you're doing some weird funky macro stuff. The right way would be to really ask the compiler to tell us what you're doing and what you're actually using. And there's flags for it, we just don't use it yet. And that would give us all the include, basically will give us the include tree, and then from there we could just look at those and decide if we want to rebuild or not. Does that make sense?
Well, I do have a follow-up question.
Yeah, no problem.
So if you ask, say, GCC to just evaluate a file, say GCC takes a minute, because there are some files where GCC will actually take over a minute to
That's a very good question. So the question was if we are going to, for a scenario where GCC would take a long time to process the file just to give us what's the tree of included, are we looking into rolling out our own LLVM or things like that, specialized processing that would go faster? That case, I would say the one way that can be done is we're not going to always just ask the file and tell us our task graph. It's just the first invocation, we won't have any information, so we're going to assume it's out of date and just ask to be built. And then during the building, it's going to give us the task graph, well, not task graph, but the graph of the include. And then the subsequent one, we can just take that and figure out, is there any file in there change? Yes, then we can follow the path and know what file needs to be compiled. But it is something that we entertain into, specifically for the caching, if we can avoid doing a compilation or pre-compilation or just like touching the file, if we can just try to shortcut even more by having something like LLVM shortcut. I cannot say at this moment where it's going. It was just a preliminary discussion of how caching is going to be implemented for native. So that's going to come up in the future, but definitely that is a possibility of on the table for handling those cases. Is there another question? You have a question? Or okay, perfect. So yeah, don't hesitate to follow me on Twitter or follow me on GitHub. If you guys want to just see what I'm up to. I'm not a huge Twitter fan of posting, but you know, I might post some stuff here and there. And on that, thank you very much. And that's the end of the conference. Well, congratulations, everyone.